Good day, everyone. This is going to be the video lecture for Physics 1000 Chapter 7. Chapters 7 and 8 are going to be our two chapters on, excuse me, 7 and 8 will be our chapters on heat and thermal energy and various thermal processes. Chapter 7 is going to be mostly concept focused on a lot of the concepts involving heat and thermal energy. There will be some math, but there's going to be a lot of concepts we're going over. So the homework will also be pretty heavily concept-based, just to make everyone aware of that. Let's just go ahead and get started. If you are going through the slideshow with me, first slide, Chapter 7, Thermal Physics, is just the title slide. Slide 2, we get started on content. We're going to be talking about everything to have to do with heat and temperature. All boils down to something called thermal energy. And energy in general is something that cannot be created or destroyed. It simply takes on many different forms and can be possessed by many different objects. We've talked about various forms of energy before. If an object has kinetic energy, then it is currently in motion. So when I throw this tennis ball, it has kinetic energy, it is moving. If I elevate this ball to a position where it could be falling, it has energy stored within it as gravitational potential energy. That energy is then released when the object is allowed to fall. So across the board, energy is just, it's something that objects can have that allows them to do something. It's not really, you can't really see energy itself. You can only see what objects with energy are able to do because they have energy. You can never see the energy, but you can see that the ball is moving because it has energy. Thermal energy is a very good example of this. Kinetic and gravitational potential energy are types of energy we call mechanical because they all have to do with physical, mechanical things. You can see the ball mechanically moving. It can mechanically interact with other objects as it moves. If I elevate the ball, I have mechanically moved it through 3D space. These are mechanical because they are physically affecting systems that we can directly observe and interact with. Non-mechanical forms of energy is what energy types that are non-mechanical are harder to see and to directly observe. And thermal energy is a type of non-mechanical energy. So in one of our previous chapters, we talked about collisions, specifically collisions, different types of collisions where energy is either conserved in the collision or it isn't conserved in the collision. Now, in an elastic collision, the kinetic energy is conserved because this elastic tennis ball can bounce against something, store its energy within itself, and then release it when it stretches back to its normal size. But in an inelastic collision between an object that is not elastic, like, well, I have this roll of tape on me. This roll of tape is not elastic, so when it collides with something, it's not able to store that energy inside of itself, and so this is an inelastic collision where the kinetic energy in the collision is not conserved. It's no longer in a kinetic mechanical form. It can't be destroyed. It's just not in an observable mechanical kinetic state anymore, which means it has become a new, different type of non-mechanical energy, namely thermal energy. In a lot of collisions, in a lot of inelastic collisions, a lot of the energy lost in the collision actually becomes thermal energy inside of the objects that collided. Now, if you move on to slide 3, we're going to talk a little bit about what thermal energy actually is and what it means when an object has it. Thermal energy, if an object possesses thermal energy, it will begin to warm up. Objects that possess more thermal energy tend to be warmer. It is a form of energy, so when matter has energy, it is then able to do something. Now, when matter possesses thermal energy specifically, the particles that make up that matter, if you'll see on slide number 3, all of those dots represent the atoms inside of an object. The more thermal energy an object has, the faster its particles are going to move. If you'll recall from kinetic energy, an object that is moving faster has more kinetic energy. It's the same with thermal energy and the movement of individual molecules. The faster an atom is moving, the more thermal energy it has. So the hotter something is, the more thermal energy it has, the more its particles are moving around. Meanwhile, the colder something is, its particles are not moving around as much. They're slower, they have less thermal energy, and they're more stationary. This is what leads to phase change. You've all interacted with water in the form of water, but also in the form of ice and in the form of steam. If you start from ice, ice is very cold, so it has less thermal energy than the other states that water can have. The particles that make up ice, they are very cold. They don't have a lot of thermal energy, so they're not moving around a whole lot. They're stationary. They're locked in place. When you warm up that ice, when you add thermal energy into the ice, its particles will begin moving around a little bit more. And if you move on to slide number 4, you'll see that as particles in a single object move around, they will also tend to bounce off of one another more. As the particles move more, they will naturally collide with one another more. So as an object warms up, as you add thermal energy into an object and it begins warming up, its molecules, its atoms will begin moving around more, they'll begin colliding with each other more, and as that happens, the particles naturally sort of drift farther and farther apart. Like, imagine you had a big old bag full of ping pong balls. If you hold the bag still, and the ping pong balls are not moving, they don't take up a whole lot of space. But when you shuffle the bag around and the ping pong balls are all bouncing off of one another, they fill up the whole bag. As long as you keep it moving, those ping pong balls are bouncing every single place that they possibly can, and it looks like they take up more space until you let them slow back down. So the warmer something is, the more thermal energy it has, the more its particles are moving around, the more they collide with one another, and eventually those particles will start drifting farther and farther apart. In the case of ice, as the ice molecules begin drifting farther and farther apart, eventually they get so far apart that the ice can no longer maintain its solid shape, and it melts into water. So the particles in water are farther apart from each other than the particles in ice. And if you keep heating up the particles in the water, they'll keep getting faster, bouncing off of each other more, getting farther and farther apart, until eventually they're so far apart they become steam. So, thermal energy, when an object possesses thermal energy, its particles begin moving around more, bouncing off of each other more. Eventually, this causes them to drift apart, and if you add enough thermal energy to an object, that can induce a phase change. Phase change is what we call the act of an object changing its phase, like melting, boiling, freezing, condensing. So, moving on to slide 5, we're just summarizing some of these points again. The collisions between individual particles inside of an object result in work being done. It's like the collisions we studied before. If I was to throw something at this dinosaur, within this collision, work is done from the ball and the dinosaur because the ball exerts a force on the dinosaur for some distance, and there's a transfer of energy between the two objects. This is what happens every time you touch anything. When you touch something and you think, oh, that feels cold, or oh, that feels hot, what's happening is, so say I am touching this cold, my thermos will stand in as a cold object. When I touch my thermos, the particles of my finger are colliding with the particles of the thermos. Just like how normally, when you heat up a single object, its particles begin colliding with each other. If you touch something else, your particles will begin colliding with that object. Right now, there's a bunch of collisions going on between my finger, between the atoms of my finger and the atoms of the thermos. As a result of my particles colliding with the thermos's particles, there's going to be work being done in those collisions. Now, if I am warmer than the thermos, if I have more thermal energy than the thermos, my particles are more energetic than the thermos is. That means that when my particles hit the thermos's particles, the energy is going to transfer from me into the thermos. If I'm warm and the thermos is colder than I am, the energy in me, when my particles collide with the thermos's particles, energy is going to exit my body and enter the thermos. That's going to make me colder because I'm losing thermal energy, but it's going to make the thermos warmer because it is gaining thermal energy. This is a heat exchange, a heat transfer. Specifically, it's happening because I am touching the thermos. This is called thermal contact. It's what happens when two objects are in physical contact with one another, and there's an exchange of thermal energy from one side to the other. So, temperature, heat is all due to thermal energy. When objects possess thermal energy, their particles move around, they're bouncing off of each other, they're drifting farther apart, they are colliding with themselves and with other objects that you are touching and in thermal contact with. The more thermal energy you have, the higher the speed the particles are moving at, the more collisions there are. And heat, thermal energy will always transfer from hot to cold. It always goes from hot to cold, because cold is just the absence of thermal energy. There's no thing you can give to an object to make it cold. Cold is just the state where an object does not possess thermal energy. You gain thermal energy to make yourself warmer. You lose thermal energy to make yourself colder. Whenever you feel cold, whenever you touch something and you think that is cold, you're not feeling coldness enter your body. You're feeling thermal energy leaving your body. So when you think this feels cold, you're feeling thermal energy leave your body to enter the object that is at a lower temperature. Whenever you feel hot, whenever you touch something and you think, oh, that's hot, that means what you're feeling is thermal energy entering your body from the warmer object. This, if you move on to slide number 6, is due to heat transfer. All energy cannot be created or destroyed. There's a certain amount of energy in the universe, there's a certain amount of energy within a system. That total amount of energy cannot change, but that energy can change where it lives. It can change what object possesses it. And so using heat transfer, you can take thermal energy from one object and give it to a different object. The same total amount still exists, you've just changed what object has how much of it. There's 3 different ways you can transfer heat between different objects. The first way is through thermal conduction. That is when you just simply touch something and heat conducts physically from one object to the other. It's a lot like conducting electricity. You touch something, if there was, electricity running through this water bottle and I touched it, I would get shocked. Heat conducts a lot like electricity does. If I touch something, thermal energy begins flowing through that connection like electricity could flow through that connection. There's also convection as a means of heat transfer, and this is how your oven works. This is how boiling water works. When objects heat up, their particles bounce off of each other and tend to drift apart. In general, that means that something that is warmer will be less dense than when it was colder. If you've ever heard the term hot air rises, this is what creates that phenomenon. Hot air, if you've got just a bunch of hot air right here, because its particles have drifted farther apart than when they were colder, it's now less dense than the cold air around it. And an object that is less dense than the fluid surrounding it is going to begin floating. So hot air is going to rise because it is less dense than the cold air around it. And as that hot air rises, it's bringing all of its thermal energy with it. So the way that your oven works is most ovens, I'm just going to draw a little box oven right here. Most ovens have heating coils in the bottom. So when you turn the oven on, you can see the coils glowing in the bottom. Sometimes there's little flames at the bottom. Point is, there's something hot at the bottom of the oven. These coils are going to heat air at the bottom. That air is going to rise because hot air is going to rise. It is less dense. As it rises, it's going to touch all the cold air up here. So that rising hot air is going to begin cooling down. It's also going to touch whatever you put in the oven to cook. So this is just going to be a poorly drawn turkey. So this hot air is rising. It's touching the turkey. It's touching the cold air. So this hot air is bringing heat up with it. It's going to touch things that are colder than it, and that heat is going to transfer out of the hot air and into the cold air and into the turkey. That's going to cool the air back down. Once it's colder, it's going to sink back down to the coils. Now that it's touching the coils, it's just going to heat back up and rise again. As it rises, it's going to transfer heat into the turkey. It's going to transfer heat into the cold air up here. And so once it's cold, it's just going to sink again. And that process is just going to keep continuing. This is how we get heat from the coils in the bottom into your turkey to let it cook. And the same thing happens when you're boiling water. Water and air are both fluids. You can convect heat through any fluid. So convection is conduction with a few extra steps. Lastly, you can also transfer heat through radiation. And this is how we get warmth from the sun. Notice the sun and the earth are not in physical contact. The sun is very far away from the earth. In order for us to be warmed by the sun is basically shooting lasers at us all the time. It is shooting light and other forms of radiation at the earth. That radiation is energy, and so when all of those rays strike the earth, we get energy from them in the form of thermal energy. So that method of radiation, being able to transmit energy through a vacuum, is how we get energy from the sun. You can also see this in heat lamps at restaurants. That uses radiation, the light and the rays from the lamp beaming down on the food, to send thermal energy into the food to keep it warm. Excuse me. Moving on to slide number 7. Some general rules. Again, heat is always going to transfer from hot objects into cold objects. Again, there's no cold energy. You either have thermal energy and you're warm, or you don't have thermal energy and you're cold. The thermal energy, like a lot of things, wants to go from areas of high concentration to areas of low concentration. So thermal energy always goes from hot to cold. And if any two objects are touching for long enough, eventually enough thermal energy is going to leave my body and enter the thermos to get to a point where we are at the same temperature. Once we're at the same temperature, the energy will stop flowing, because now that we are balanced, there's no reason for the heat to exit me anymore. When two objects are in thermal equilibrium, the flow of heat between them will stop, because you cannot go from hot to cold if the two touching objects are at the same temperature. So, if two objects are at the same temperature, they are in thermal equilibrium, and the heat between them will stop flowing. If two objects in thermal contact are at different temperatures, heat will flow between them. Again, if you touch something cold, thermal energy is going to exit your body and enter the cold object. That is heat flow. That is energy transfer. Okay, so we measure the amount of thermal energy an object approximately has using temperature. Now, temperature is not directly a measure of thermal energy. Temperature sort of tells us the average thermal energy level of an object, but it does not directly tell us thermal energy level. For example, a very large object, like a giant boulder, might be at the same temperature as a pebble. But because the boulder is so much bigger and has so much more mass, it has a lot more thermal energy inside of it. So temperature tells us the average thermal energy level of a whole object. It doesn't directly tell us how much thermal energy it entirely has, just the average. But it's still a very useful tool, because if one object has a higher temperature than a different object and they begin touching in thermal contact, we know for certain thermal energy is going to exit the higher temperature object to enter the lower temperature object. And again, that describes it both ways. If a cold object touches a hot object, thermal energy will enter the cold object from the hot object. So even though temperature doesn't tell us all of the thermal energy something has, it still tells us it still gives us that average and helps us to compare that temperature to other objects. It is a relative measurement. It doesn't tell us, again, total level, but it's still very useful. Slide 8 summarizes this information. Slide 9 shows the 3 different temperature scales that are commonly used in physics. They are Fahrenheit, Celsius, and Kelvin scales. Here in the United States, we tend to use Fahrenheit a lot in our day-to-day lives. For Fahrenheit, the boiling point of Fahrenheit, the point at which water boils, is 212 degrees. Meanwhile, the freezing point of water is 32 degrees Fahrenheit. Physics doesn't use this one super often because those temperatures are kind of a little bit wonky. And so physics more often uses the Celsius scale. 100 degrees Celsius is when water boils. 0 degrees Celsius is when water freezes. Celsius is preferred by physics because it's easier to remember, 0 and 100 instead of 32 and 312, and everything sort of goes in those nice intervals of 10 all the way from 0 to 100. But it's still not perfect. If you've lived, even here in the South, we sometimes have days that is beneath freezing. We have days that are colder than freezing, often enough. So if you checked the weather and the temperature was given in Fahrenheit, if 32 is the freezing point of water, we've had days of like 30 Fahrenheit, 25 Fahrenheit. Those are below freezing. If you look at the equivalent in the Celsius scale, those would be beneath 0 degrees Celsius. So the problem with Celsius is it sets 0 as the freezing point of water, but things can still be colder than that. So 0 Celsius is a really bad indicator of how much thermal energy an object can have, because objects can get much, much colder than 0 Celsius. And that's why the Kelvin scale was invented. In the Kelvin scale, so I have all these numbers written up on the board. In the Kelvin scale, scientists figured out what the absolute coldest temperature anything could ever be was. The coldest temperature any object can ever be, we call it absolute 0. And the Kelvin scale set that lowest temperature at 0 Kelvin. They then decided, okay, we're just going to scale up from there. If the freezing point of water, freezing and melting points are the same thing, because at 0 Celsius, ice can melt into water and water can freeze into ice. They started from the Celsius scale and realized absolute 0 was 273 degrees lower than that. So, for their Kelvin scale, absolute 0 is now 0 Kelvin, And the freezing melting point of water is now 273 Kelvin. Notice it's not degrees Kelvin. Over here I've got degrees Fahrenheit, degrees Celsius. We don't put degrees in front of Kelvin for some reason. It's just K for Kelvin with no degrees symbol. Now, 1 Kelvin is the same size as 1 Celsius, which means since there's 100 degrees Celsius between melting and evaporating, there's also 100 units of difference between melting and evaporating in the Kelvin scale. So in the Kelvin scale, melting happens at 273 Kelvin, evaporating happens at 373 Kelvin. Those are scaled 100 apart like in Celsius, because Celsius degrees and Kelvin are the same size. That's done by design. However, there's 180 degrees between melting and evaporating for Fahrenheit. 1 Fahrenheit degree is not the same size as 1 Celsius or 1 Kelvin. That's something to be aware of. And it's evidenced in the conversion equations we're going to talk about now, actually. We have these 3 temperature scales. If you move on, so slide 8 introduces temperature, slide 9 shows the scales, slide 10 now shows the formulas for converting between the scales. So, if you want Fahrenheit and have Celsius, what you want to do is you're going to take your Celsius temperature, multiply by 9/5, and then add 32. And that is how you convert from Celsius to Fahrenheit. You can also use algebra to start from Fahrenheit and convert to Celsius. If you want to convert from Celsius to Kelvin, you just have to add 273. Conversely, if you... Yes. Conversely, if you have Kelvin and want Celsius, you're going to want to subtract 273. So these are your formulas for converting temperature scales. We're going to use them in a second. Slide number 11 mentions the example I talked about a second ago. An object's temperature does not tell you absolutely the amount of thermal energy that's in it. A lot of if you have 100 of something at the same temperature, there's more thermal energy combined in all of those than there is in just one of that something. This on slide 11 it talks about individual cups of coffee. Earlier today I talked about comparing a boulder to a pebble. The more mass might be at the same temperature as the less mass, but it takes more thermal energy to get the larger mass at the same temperature. So again, temperature tells us the average. It tells us whether or not energy will leave or enter that object when it touches an object of other specific temperature. So keep that in mind when you're doing your temperature equations, when you're looking at temperature as a measurement. So we're going to utilize these formulas to do some quick sample conversions. So our first set of problems, the first one gives us 45 degrees Celsius and asks us to translate that into Kelvin and Fahrenheit. So let's start with Fahrenheit. If we're starting with Celsius, we're going to do 9 over 5 times our Celsius. So 9 over 5 times 45 plus 32, and that's going to give us our temperature in Fahrenheit. If we want Kelvin from Celsius, we're going to take our Celsius and add 237. So 45. So I'm going to make note. This is putting it in Fahrenheit. This is putting it in Kelvin. 45 plus 273. And that's going to give us our answer there. Go ahead and calculate these answers. I recommend entering things into your calculator as shown on the board. We'll check our answers on the next slide in a second. Now, The second question gives us degrees Fahrenheit, and we have to find Celsius and Kelvin from there. So 2. I'm going to recommend we find Celsius first, because we need Celsius to be able to find Kelvin. So we're going to convert from Fahrenheit to Celsius. So we have 45 Fahrenheit. We want Celsius. So C is still left as it is in our formula. So we have 45 equals 9/5 times C plus 32. So what you're going to have to do here is subtract 32 to the other side, then multiply both sides by 5/9. I'll go ahead and write that next step to help everyone visualize that. So I've subtracted 32 over to the other side. Now to get C by itself, you need to multiply both sides by 5/9, and that will get you C by itself. I'm going to go ahead and find what that C is because we need it to find Kelvin. So I'll show you what I put into my calculator just to get that answer. You get 45 minus 32. Press enter. That gives us 13. We're then going to multiply that 13 by 5/9. We're going to multiply both sides by 5/9 so that it cancels the 9/5 on this side. And that's going to give us 7.2 degrees Celsius. Still above freezing. Now that we know Celsius, we can find Kelvin using it. So to find Kelvin, we're going to take our 7.2 and add 273, and that will tell us our Kelvin. Now the last one, we've got 45 Kelvin. We want to find then Celsius and Fahrenheit. I'm going to recommend we find Celsius first so that we can then use the Celsius to find Fahrenheit. So Kelvin equals Celsius. Whoop, sorry, we're starting with Kelvin. My apologies, I had things a little backwards. So Kelvin equals Celsius plus 273. So we have 45 equals C plus 273. We're going to want to subtract the 273 over to the other side. That should give us a Celsius temperature of negative 228. That is a negative. That is intentional. That is on purpose. This is below freezing. This is very, very cold. Keep in mind for the Kelvin scale, 0 Kelvin is absolute zero, the lowest temperature imaginable. That temperature is 273 degrees below the freezing of water. If you have ever experienced, there is no way for you, a human, to experience a temperature anywhere near absolute zero. You will freeze solid immediately. This is super cold. 45 Kelvin is colder than anything you will ever experience in your life. So once we have our Celsius, Fahrenheit is equal to 9/5 times the Celsius temperature plus 32. I will put that into my calculator to show you guys how to do it. 9 divided by 5 times negative 228 plus 32. So I've got that all in my calculator in one step. Make sure you're only multiplying the 9/5 by the negative 228. Make sure the negative is only on the 228 and the parentheses, and then add the 32. And that will give us our Fahrenheit temperature, which is also very, very cold. To check all of your answers, move on to slide 13, and this has all of the answers on it. Make sure you can get all of these answers on slide 13 from these formulas. Make sure you can get those answers to be able to move forward. Okay? Let me know if you have any questions doing so. All right, so an object's temperature will change as thermal energy either enters it, which will make it warmer, or leaves it, which will make it colder. Now, moving on to slide 14. When thermal energy changes, when an object either has thermal energy enter it or leave it, that is known as heat. Heat is defined as the change in or the transfer of thermal energy due to a temperature difference. Heat itself is not actually a thing. Thermal energy and heat are not the same. Thermal energy is the energy type. Heat is what happens when thermal energy changes. It's a little bit confusing, the terminology there, but remember that heat is a process. Heat is a process. Whenever thermal energy transfers between objects, thermal energy is changing between those two objects. If I touch this cup, my cold thermos, 10 joules of thermal energy might exit my body and enter the thermos. So I lost 10 joules of thermal energy. I lost 10 joules of heat because in this case the thermal process of heat meant I lost 10 joules. Meanwhile, the thermos is going to gain 10 joules. So again, energy is always going to flow from hot to cold. This thermos is colder than I am. It's metal. It's filled with cold water. So when I touch it, thermal energy will exit me and enter it. And that's going to cause the temperature of me and the temperature of the thermos to change. Now, we measure, the thermal energy is a type of energy, and heat is the change in thermal energy. Therefore, thermal energy is measured in joules, because it's a type of energy, and joules is what we measure energy in. It's the unit of energy. And because heat is the change in thermal energy, heat is also measured in joules. So we're going to use as our variable for heat Q. Q is heat. Heat is measured in joules. It is the change in thermal energy. Thermal energy is also measured in joules. Another unit of thermal energy that is used commonly in biology and chemistry is the calorie. So when you eat food, the calories in the food you're eating is literally the energy in the food you are eating. And your body, you take in that energy in the form of chemical energy stored in the bonds of the food. Your body then breaks down the bonds in the food and releases that energy as thermal energy and other types of energy into your body. And so calories is just another unit of energy. Something to be aware of though, the number of calories on like the box, like when you read a box, a product box at a grocery store, the food calories on that box, like if you buy something that says contains 100 calories, that is calories with a big C, which is not the same as the small heat calorie that is mentioned on slide 15. That would be, the food calories are actually kilocalories, which are 1,000 times bigger. That's something to be aware of for your dietary needs. For this class, we're going to stick to joules for our energy units. We're going to stick with joules. Joules is what we've been using. Joules is what we're going to keep using. Slide 16 just shows more example of heat transferring due to differences in temperature. And then slide 17, we're going to go over the second and last formula of chapter 7, and that is the specific heat formula. We're going to talk about we're going to quantify now the amount of thermal energy changing in an object based on its temperature change. So, when an object loses or gains thermal energy, its temperature is going to change. If I lose thermal energy, I'm going to get colder. And this formula right here, the specific heat formula, is how we calculate that. So, this is the specific heat formula. Q represents heat, that is the change in thermal energy. So if I lose 10 joules of thermal energy, that would go here. So the change in thermal energy of an object, the heat, is equal to mass, the mass of the object. So if I'm the one losing thermal energy, we would put my mass right here. I'm going to get to C in just a second. I'm going to explain C in a moment because it's the tricky one. We've got Q equals M times delta T. So delta T is the change in temperature. The more my temperature changes, the more my thermal energy has changed. If I lose 10 joules, my temperature might drop by 1 degree. If I lose 20 joules, my temperature might drop by 2 degrees. The amount of thermal energy you lose will determine your temperature change. That's what this formula tells us. Now, you have to be very specific about what units of temperature you plug in here. It does have to be change in temperature. It is delta T. That's final temperature minus initial temperature. So your temperature begins at something before you gain or lose heat, and it's going to end at something else after you gain or lose heat. This is delta T for the change. And you can only plug either degrees Celsius or Kelvin into this formula. Both of them work only because their units are the same size. If you increase in temperature by 1 Celsius, you also increase in temperature by 1 Kelvin. They're the same size as one another. Fahrenheit units are a different size. Fahrenheit units are about twice as big. Remember, for both Celsius and Kelvin, there's 100 degrees between freezing and evaporating, but for Fahrenheit, there's 180 degrees between freezing and boiling. So now that doesn't mean that water is going to boil at a different point. It just means that the numbers are different. So because of that offset in the size of the unit, you do have to only make sure you plug in Celsius or Kelvin into this formula. Make very careful of that. Either one works, but you cannot use Fahrenheit. Now the last variable in this formula is C. C is the specific heat of the object you are examining. Now specific heat is a measure of an object's, it sort of tells you the thermal properties of a unique and specific type of material. I imagine you've all gone outside on a hot summer day, and say you're going to the beach or the pool. You get out of the car, your shoes are already off because you're going to run into the water. Your shoes are off, and the very first thing your bare feet touch is hot concrete. It burns, it's not fun, you don't like it, so you immediately jump from the hot concrete into the grass. And it's colder. The grass is at a lower temperature than the concrete, you don't burn. Now, both the grass and the concrete, they're exposed to the same temperature air, they're both out on the same summer day, and they're both getting the same light from the sun. So why are they at different temperatures? Why is the concrete hotter than the grass? You might also notice this getting into your car on a hot summer day. You get into your car, you can sit down on the seat just fine, and then when you reach for your seat belt, you touch the metal of the clip, and the metal is super hot. The metal's at a high temperature, but the rest of the plastics and the leathers and the other materials in your car are okay to touch. For some reason, it's just the metal that's at a super high temperature. That's due to differences in specific heat. Specific heat measures an object, how much an object's temperature changes for a certain amount of energy gained or lost. Some materials don't change temperature very quickly, especially water. Water has a very high specific heat. That means it needs a lot more thermal energy than, say, metal in order for its temperature to rise by the same amount. Now, table 11.1 on slide 17, the slide with this formula on it, that table shows various specific heats for various different types of material. You only need to pay attention to the joules per kilogram degree Celsius category. You don't need to pay attention to the calories column, but notice the numbers in the joules per kilogram degree Celsius category. All these materials have different specific heats, and the materials that heat up faster on those hot days have smaller specific heats. Things like the metals, like aluminum, cadmium, copper, iron, lead, mercury, silver, and tin. Those are all metals, and they have lower specific heats on this table, somewhere from like 100 to 1,000. Meanwhile, liquid water has the highest specific heat on this table, 4,186. Out of all the materials listed, water needs the most heat in order for its temperature to increase. Different materials will require different amounts of thermal energy to increase their temperature by the same amount. This, in general, is a very good thing for life on planet Earth. Since grass is mostly water, that's the reason why the grass is colder than the concrete ground. Even though the grass is still exposed to the same temperature air, even though it's still getting the same amount of sunlight from the sun, it's not heating up as fast, which keeps it at a lower temperature, which makes it easier for you to stand on. This is also the reason why whenever you jump into a body of water during the summer, jump into the pool, jump into the river, jump into the ocean, it's always usually colder than being standing on the sand in direct sunlight, because it takes a lot of thermal energy for that water to warm up, which is very good. If water had a lower specific heat, if water heated up faster, our oceans would boil just from being in sunlight. Life on this planet is only possible because water has a high specific heat. So, what you need to know about specific heat is it represents how much thermal energy a specific material, how much thermal energy a specific material needs to change its temperature. And it's going to depend on the material. You have this table here ready to check for your specific heats. You have this table. This table of constants is known to you. You will be told, either you will be told what material you need to look up, or you'll be given enough information to solve for this specific heat. These are all known constants, even though every single material has a different one. You're not going to have to memorize any of them. You have the table is at your disposal. I'll make sure it is readily accessible during tests and future assignments. Let's utilize this formula really quickly as we close out these notes. So, a metallurgist is someone who studies metals. It's a metal scientist. Heats up a 100-gram sample of lead, up. So I'm going to go ahead and start listing variables here. We have mass of lead is 100 grams. Mass of lead is 100 grams. This sample is heated up to a final temperature of 800 Kelvin from an initial temperature of 25 degrees Celsius. This is room temperature in the Celsius scale. Room temperature in Fahrenheit is about 75 Fahrenheit. Room temperature in Celsius is about 25 degrees Celsius. Just something to keep in mind. And what we are asked to find is how much heat was added to this metal to make this happen. So, what we want is to know the heat added to our sample. If we look at our new formula, heat equals mass times specific heat times change in temperature. We know the mass of our lead we know how much the temperature changed. We know its initial state. We know its final state. We want Q. That means we want Q. We know M. We know T. We need something to use for C. Now the problem says that this sample is lead. So you can go onto your table right there, your table 11.1 on this very slide, to look up what the specific heat of lead is. And that table says the specific heat of lead is 128, my 8s look a little funny, just rewriting that, joules per kilogram degree Celsius. So that table has told us our specific heat for lead. This is our C. We can plug this into our formula. So we're ready to start plugging everything in. We are solving for heat. We want to know the heat added. We're going to plug in the mass of our lead. We have a 100 gram lead sample. Now keep in mind, our standard unit for mass is actually kilograms instead of grams. So 100 grams is going to be 0.1 kilograms. Next we plug in C. We got 128 from our table. And now we plug in our change in temperature. So we end at 800 Kelvin and we begin at 25. Delta is always final minus initial, so I'm subtracting the final temperature from the initial temperature. But there's a problem. These two temperatures are in different scales. One is in Kelvin, one is in Celsius. Both of them need to match. They need to match in order for us to be able to work this problem. So, what I'm going to do is I'm going to convert Celsius into Kelvin. Our formula to get Kelvin from Celsius is just to add 273. So, I'm going to take our 25 and add 273 in my calculator. That's going to give me 298. So, our initial temperature in Kelvin is 298. This is likely the temperature you're experiencing right now. This is average indoor temperature in the Kelvin scale. Something to keep in mind, just to sort of set in your head your expectation for numbers in the Kelvin scale. So, our initial is it is 25 Celsius, but we've converted that to 298 Kelvin. So, these units match. 800 minus 298 will tell us the change in temperature, multiplied by C, multiplied by mass, and this will tell us how much heat needed to be added to the lead to make this happen. So, just going to put everything into my calculator and show you. So, it spills over onto two different lines, but we've got 0.1 times 128 times, now I've got open parentheses, 800 minus 298, close parentheses. So make sure that those are both together in a single set of parentheses so that the subtract operator is only done on that 2 and then everything is multiplied together. Press enter and that will tell us it took 6,425.6 joules of thermal energy to be added for this lead's temperature to increase by that amount. And that is the specific heat sample problem. Well done, everybody. Again, keep in mind, delta always means final minus initial. It's very important. If your final temperature is lower than your initial temperature, you're going to get a negative answer for Q. That's fine. A negative Q tells you that you lost thermal energy. The object you were looking at got colder, thermal energy has left it. That's what a negative Q would mean if your final temperature is lower than your initial temperature. And our Q, our thermal energy, our heat, is in measured units of joules. So, great job, everybody. One last detail, just one tiny addition in terms of concepts. If you look on slide 19, just a little bit of information about how phase changes work. When you add thermal energy to an object, its particles begin moving around more, they're bouncing off of each other, they'll eventually space farther apart. That is the process that induces a phase change. Now, the temperature at which a phase change happens is the temperature at which both of those states can exist at the same time. If you look at the graph on slide 19, notice you begin with ice at the very bottom. You can increase ice's temperature up to the melting point at 0 Celsius. At that point, it begins to melt. Now, ice is not going to once you get ice up to 0 Celsius, it doesn't immediately become water. It's a slow process. If you take ice out of your freezer and now it's in room temperature air, it does not immediately become water. It slowly begins melting. That's because the temperature of the melting point, of the freezing point, is the temperature at which both the solid and the liquid form of that object can exist at the same time. You can have 0 degrees Celsius ice, you can have 0 degrees Celsius water. The temperature does not begin changing again until the phase change is complete. Once all the ice is melted, you now have 0 degrees Celsius water, and then that water's temperature can begin rising. As the water warms up, it'll eventually get warmer. Its particles will get farther apart, so far apart that it'll begin turning into steam. At 100 Celsius, you can have water and steam at the same time. When you boil water to make your pasta, once it gets up to boiling, it does not immediately entirely turn into steam. It takes time. All that slow bubbling, all the steam coming out of it is the slow process of the water slowly turning into steam. Once all the water is evaporated, it will then be 100 degrees Celsius steam, and then you can keep warming it up past 100 degrees Celsius. And slide 20, additional information about melting, freezing, condensing, boiling. If a process is endothermic, that means it is absorbing heat. When something melts, it is absorbing heat from the environment to become warmer. When something boils, it is absorbing heat from the environment in order to become hotter. That actually makes the environment around the object colder. So when you put ice in your drink, as the ice melts, the ice gets hotter, but everything the ice touches is getting colder. Similarly, a process that gives off heat is called exothermic. It is giving heat out of itself, and that makes the environment around it warmer. Freezing is technically a warming process, an exothermic process, because the water gets colder as it freezes into ice. That means everything around it gets warmer. If my freezer is at 0 Celsius and then I put something into that freezer that's at 25 Celsius, the 25 Celsius object will begin cooling down, but as it gives off heat into the rest of the freezer, everything else in the freezer is going to warm up for a little while as that thermal energy from the warm object is distributed amongst everything in the freezer. So, just something to be aware of about phase change. That is everything from Chapter 7. The assignment for this is going to go up pretty soon. Please come prepared. Come to the class calls with any questions you have on these notes, the homework, the quiz, the labs, the upcoming test, anything. I'll have examples. I'll be able to help you through anything that you're going through. Speaking of test next week, I originally said our test is going to be on the 19th of this week. I have decided to move it to be able to be taken on the 22nd or the 23rd of next week. That is Monday and Tuesday. So this week we're going to be closing out these examples. We're going to be closing out Chapter 9 and Chapter 8, and next week the test will open up for you guys. So come to our class calls to make sure you are ready for everything involving Chapter 8, Chapter 7, and the test next week. Thank you all very much, and I hope you have a great day.